No, madam.
No, it's
Okay.
not visible.
Can you see now?
Yes.
Okay. Thank you. Okay. So I'm really happy to be a part of this session today. So let me introduce myself. I'm Jinu Jacob. I'm presently working as a geotech engineer in Nextracker, which is a US company based on solar trackers. My previous experience is with L&T construction, where I was working in water treatment sector, and there I have worked 4.5 years, where I was using Plaxis 2D software in my works. So by this session, I think we'll be able to get some idea about the software usage, and for some basic problems, even every one of us can be using this software. So let us move on with the session. And Plaxis 2D is developed by Bentley, and if we want to get the software, we have to contact Bentley Systems. So the overview of my presentation will be, we'll just see an introduction to Plaxis, then what are the key benefits of using Plaxis, then we'll see a problem definition, and we'll see a modeling using Plaxis 2D, and then we can go for the discussion. So Plaxis 2D is, as the name says, it's a two-dimensional modeling. So similar way, there is Plaxis 3D, which is used for more advanced like tunneling, or if we need more detailed engineering works, we'll go for Plaxis 3D. And there is some other Plaxis Modeto, which is specifically for groundwater flow related details. So Plaxis 2D will be solving most of our geotechnical problems. So it's a widely used geotechnical software throughout the world. That is the main advantage. If we learn it, we can use it anywhere. And it's used to perform deformation, stability, and flow analysis. And if we see the applications, excavations we can model, embankments, foundations, tunneling, mining, etc. And the main benefits of Plaxis Studio is that the interface is very user friendly, and we can easily create the models, and different structural elements can be modeled like piles, angers, geotextiles, and we can assign whatever loads or displacements we have. And there are different material models available. Okay, so just we'll move on to our problem. So in this image, what we can see is an excavation. So here we can see there is an excavation with some slope, there is some bottom width, and further it's excavating. So we are going to analyze what is the stability of this slope if we are excavating. So we will have this kind of excavation works. Suppose if we have a tank construction here, then we will excavate to the bottom and then go for the construction if we have enough space. So, or if we are going to construct a long canal, then this excavation goes on continuing. So such conditions we are going to analyze. So since it's a 2D problem, we need to get a, section of this. So if we cut a section here, be getting a profile like this. So it's having a ground level, a bottom level, and this is the excavation slope. Say our excavation depth is 6 meters, and the bottom width, what we have seen, is 10 meters. And the slope is 1.5 horizontal, 1 vertical. So this is like, if we are proposing an excavation work for some construction, then we are taking this as a initial trial. So we will check whether the slope is stable. If it's not, then we have to increase the slope, or we have to flatten it so that it will be stable. So let us take this example, which is 1.5 horizontal, 1 vertical. So to model this profile in Plaxis, we need to get these points. So to identify those points, we need to put a geometry line. It can be taken in the center or the edge, anywhere. The idea is that we need to put some coordinates for this. So the method what I use is taking the center of the excavation as a 0, 0 point. This will be positive x direction, negative x direction. Here it will be y equal to 0, and this is negative y direction. Hope you're able to follow what I'm telling. Okay, so in this excavation, here, based upon the Borlock study, there are different soils identified. So, say from ground level up to 3 meters, there is a medium stiff clay layer with SPT of 8. After that, say the soil is medium dense clay sand, N value of 15. This is still 7 meters from the ground level, and it's followed by dense sand. So, this is the soil layers. This also we need to define. So here, these points of the excavation and this point where the layer is divided, that also we need to put in Plaxis. Then based upon this slope, we can, we know the bottom dimension, it's 10 by 2, 5. And the depth of excavation is 6. So minus 6. 5 minus 6, and this is minus 5 minus 6. And we have a slope of horizontal 1.5 and vertical is 6 meters. This is 3 meters deep. So based upon that, we can find out what is the coordinates. So I have identified the coordinates here. Okay. So uh, let us just take this model. Okay. So in Plaxis, we will have, this is the Plaxis 2D input program, and this is how the output program icon looks. So once we open this, it will ask start a new project or open an existing project. So we'll go start a new project, and this is a slope stability check. So I am giving slope stability. Next. Then we have to assign the type of model. It can be plane strain or axis symmetry. So as I said, if we are modeling a canal or something which is long excavation, then it is a plane strain. If in case of a coffer dam or a shaft, wherein we have a circular excavation or like in axis symmetry, only one side requires to be modeled. Then about the center axis, the same gets repeated. So it results in a circular section. So here I'm assuming it's a plane strain condition. And here we need to define the boundary. So if we see a problem, from center we have 14 meters distance to be modeled. So our boundary should be little bit far away. Then only we'll get the correct behavior. So I'm taking in the positive direction 50 and in negative direction 50. So x minimum, I'm taking minus 50, x maximum 50. And as I said, y minimum is this one, 0. I mean, y maximum is 0. And this is negative direction. Y minimum, I'm taking minus 50. Y minimum minus 50, maximum 0. Okay. So we have defined the boundary. Now what we are seeing here is the interface. This is the portion where we will be getting the model what we are drawing. Here if you see there are different tabs. Soil tab where we enter all the soil related details, structures to model the structures, mesh generation, flow and stage construction. We'll see one by one. And here if we see in file we can open project or anything. Pack project means we can just zip the Plaxis file and for sending purpose. And another thing is in help, we will have the manuals. So if we click the manuals, uh, yeah, it will open like this. Then we can have this tutorial manual. If we click it, this tutorial will be opened. It will have different examples worked out, which we can use for our learning purpose. Okay, so once we start, here it's mentioned start by using borehole tool. So here it is showing this borehole tool, create a borehole. So if I'm clicking here, there the borehole is created and I can assign the properties. So as per our problem, we have up to 3 meters medium stiff clay. So, okay, here there is water table level to be given. I am assuming water table is at ground level. So head is 0. Now add. So the first layer is from 0 to minus 3. Second layer is from -3 to -7. So next layer is -3 to -7 and up to our boundary. I'm giving the same layer. Now, if we see here, there are three layers assigned. Now, what we have to give is the material properties. So here, if we click, there is new material option. If we click it, it opens. This is the soil model tab which we have to enter. So, as I said here, top layer is stiff clay, then sand. So we need to identify what are the properties to be given. So for clay layer, maybe based upon this shear test, we will be getting the results. So based up in the soil report, we will have the parameters entered. Say I am having the first layer with undrained shear strength of 50 kPa, phi value of 0, and density of 18 kilonewton per cubic meters. And for the second layer, okay, okay, this is 3 to 7 meters. This is a typo. It's 3 to 7 meters only. Uh, we have medium dense clay sand. So here there is some clay fraction also. Because of that, the shear test is showing a C value of 10 kPa and phi value of 25 degrees and a gamma saturated value of 19 kilonewton per cubic meters. The next layer is dense sand with phi value of 35. So here I'm putting a psi value. What it means is it's a dilatancy angle. So whichever angle is more than 30 degrees, we have to put it here. So even dense sand means we have to give the dilatancy angle. And then other parameters what we need to enter is E value and mu value. E is the modulus of velocity, which we won't be having mostly in the soil report. So what we need to do is we have some correlations available in textbooks. So I usually follow Foundation Analysis and Design by Josephine Bowles. So in this textbook, there are different correlations available with SPT. So if we see sand, 500 into n plus 15 is one correlation available. So silt, 300 into n plus 6. Like that, for clays and sandy clay with based upon plasticity index also, there are some correlations available. So using these, we can arrive at this E values for the analysis. Then we need to enter the Poisson's ratio. Usually, this will be a range of value. What I usually enter for clay is zero point 0.4, for sand is 0.35. After entering these details, we need to enter the drainage condition. For sand, it's predominantly drained only, so we will have the drained condition. In clay, we have an undrained condition, so I am writing here undrained B. I'll explain it. So in this software, so first layer we are going to model now. Hope you are able to follow what I'm telling. So yeah, first layer is medium stiff clay. So since it's clay, we have material models, different material models available. Linear elastic, more Coulomb hardening soil. These are different material models available. The most commonly used is more Coulomb. Uh, in linear elastic, it's taking only elastic behavior and it's mainly suitable for stiff conditions. More Coulomb is most realistic values. So it's and also the number of inputs we have to give mostly we will be having it. So it's preferred to go for a more Coulomb model. In case of hardening soil, we need to have more detailed lab test results with more odometer test results and all. Therefore, we'll use more Coulomb, which is the basic one, which will satisfy us. Now, in drained condition, we have drained, then three undrained conditions and non-porous. Drain condition can be taken for sands and gravels. In undrained A, B, C. So in when we are selecting undrained, This software automatically will assign some stiffness value to pore water. So what happens is, for the soil, whether we are taking a undrained stiffness or a drained stiffness, which means a effective stress, that matters. So to be simple, undrained A defines both strength and stiffness, which means both Cu as well as E value will be effective values. In undrained B, this Cu is only undrained only, it's not effective value, and E value will be effective. And in undrained C, both are to be undrained, but that will take a higher stiffness parameter for the soil, because already there's a stiffness for water and we are taking full stiffness for soil. So it's preferred to go for undrained B. So just we'll give undrained B. For clay, it's preferred to go for undrained B. That we can take. Now, gamma saturated, it's 18. So unsaturated, I'm giving 17 and saturated 18. These two tabs are the main tabs what we have to enter. General and now parameters. In this, E value is 12,500. New value is zero point 0.4. SU is 50 kPa. Okay, so these are the main values. Here, whatever we are saying is like, uh, in this, we are defining only one particular E value for a layer. If we need to increment that E value along with the depth, then we can use this, but that and all is not required. And if we have any specific groundwater permeability details, and all can be entered. Okay, so mainly these two tabs only required. Yeah. So this parameter we have assigned, and we can see the first layer has got the same property, that same color represents. Now second layer is medium dense clay sand. Clay sand, it's a drained condition, predominantly sand. Gamma sat is 19, 15,000.35. C value is 10 kPa and phi value of 25. 5 is 25. Okay, so only these details we need to enter. Third layer is dense sand, drained, 18, 19, 0.35. Okay, 35, and this extra greater than 30 we have to put as dilatance angle. So for sand, I have entered only phi value, there is no C value. But what we have to notice, like, um, here the third layer is coming much below the excavation bottom. So because of that, there is not much influence going to happen because of this layer. Suppose if we had this sands layer here with phi value, then for that layer we need to give some C value of 0.5 or 1, even though it is sand, because then only the software will be running properly. If there is no cohesion assigned, it will be going to some error. So the third layer also we have defined. So all three layers soil properties are given. Now suppose we have a longitudinal canal going. So if the soil profile is differing, then we can enter another borehole and show some other layers, or we can change the depth. So then the profile will be varying in that fashion. So we can enter any number of boreholes. So now soil is done. We'll move to structures. So in structures, we need to put this profile. So these coordinates have to be entered. Here we can see different options available. So to enter the points, click here, create point. First is minus 14 0. So if I'm putting my cursor here, it's minus 14 0. And here it is plus 14 0. Instead, this command also I can enter. Here, just if we put, next is minus 9.3 minus 3, minus 9.5. Instead of, we should not put comma, it's a space. Then if we put enter, that point gets created. Minus 5, minus 6. Okay. 5 minus 6. 9.5 minus 3. So all the points, whatever we have taken, has been defined here. Now we have to just make a profile. For that, create line, just connect between these points. Usually I'll close this boundary also. Now we have defined this profile. So there is an excavator which is going to excavate this soil. So we need to apply a load because of that. Here we have create load option, line load. I am just putting near to this at 1 meters away. So just we have to click and to end it, we have to right click it. So minus 15 to minus 20. Now at default, it is giving minus 1 kPa, minus 1 kilonewton per meters. So I am giving it as 20. So accordingly, the load gets adjusted. Similarly, if we have a structure here, then we can model what is the distance of that and the load, if load in a similar fashion we can enter. So now we have seen to create the soil model and to give the structures. Next is meshing. So in mesh tab, here option is there, generate mesh. Different element sizes available. Fine means it will give more accurate results. So I'm giving fine and it's going for meshing. It will take a little time for meshing. Okay, just few seconds it will be taking. If we analyze medium or coarse for the same problem or fine, then more accurate results will be coming for the fine. So it's preferred to move for fine, but in suppose if we have a deep excavation with more structures involved, more elements means it will be taking even more time for the meshing and all. So that is one, and also the for the analysis part also, it will be taking more time. Okay, so now meshing is completed. If we want to see the mesh, we can just click here, view mesh. So the output icon, whatever I have shown, that will open up. Okay, so if we see here, this is the mesh created for the problem. So wherever we have this loading or whichever is an excavation, that point will have more closer elements, and here it will be coarse mesh at the edge of the boundaries. Okay. Now we'll move to the flow conditions. So initially, when we define the borehole, we have given groundwater table at ground level. So when we go for this excavation work of the soil, first we have to lower the groundwater table. So some dewatering method will be used like well point or deep well dewatering. So by that we are assuming it's lowered below the ground, below the excavation level. So in the next phase, I am assuming there is a groundwater level which is lowered. So this is the level. Here what I can, if we select this portion, then we can give exact coordinates. Like from this point, maybe some zero point 0.5 or 1 meters away. Zero point 0.5 will be preferred. So minus 14.50, and the bottom point, say it is lowered till 1 meters below excavation. So minus 7, and now it's minus 5. Okay, let it be. So this is the profile. Now if we select any one segment and put make global, it will be like suppose if we make a next phase, then this profile only will be getting continued. Initial phase gets applied only for that level. Okay, now we'll move to staged construction. So whatever phases we are creating here, that same will get reflected in staged construction also. So in initial phase, there is only the ground level. Initial conditions are prevailing. So if we double click initial condition, it is a K naught procedure. If suppose we have a embankment constructed over this, there is an additional loading coming, then only we need to go for gravity loading. Otherwise, it's a K naught procedure that will take the normal stress conditions. And here we can give phreatic or steady state groundwater flow. This is mainly required only for dams or wherever the flow, steady state flow is expected. Now we are defining a pure groundwater level, so it's a phreatic condition. So initially there is nothing. Now we are going for the excavation. So this is the excavation phase. So in excavation phase, it starts from the initial phase, and the calculation type here we have options of plastic, consolidation, safety. Safety is to be given only when we are going for a factor of safety check. So here it is plastic only, and yeah, only this we need to give the proper ID what for identification, and we have to check the calculation phase. Then we are checking the factor of safety. So from this level, we are going to check the excavation factor of safety. So this will be a safety analysis, and we'll click OK. So in excavation phase, this load is to be activated. We have to right click and it will get activated. In first phase, it is all gray color. Here it is activated. And we are going to excavate. So this block we have to select and right click, deactivate. So it simulates the excavation. So now both excavation is that phase is completed, and for factor of safety, this is the child of excavation phase. So the same gets repeated. Now this is just a simple model I'm going to show. So here we are calculating. It will show some warning, select nodes and stress points. Suppose if we want some specific load displacement graphs at some certain nodes, we can select it. So I don't want that. I'm just calculating. So this is the calculation window. It shows the stages of calculation. This also will take more time if there are more phases. So since it's only 3 phases, it will close very fast. Okay, it will take few more seconds. Usually the safety analysis only will take a little more time. This it's running now in excavation phase, FOS 2. Other phases, which are our excavation plastic stages, won't take much time. Okay, now the analysis is completed. We can view calculation results. Okay, so in this output, our main aim is to see the factor of safety. So here we can select the factor of safety stage, and in the project calculation information, we can see what is the safety factor. It's having 1.43. So this is higher than 1.2. 1.2 is our limiting factor of safety. So it's safe. Another thing is we can see what are the deformations associated with this excavation. So here this is like total displacements. In deformations, total displacements, there is ux uy. So uy means vertical displacements alone we can see separately. So this way we can just model and see how it is. So I think the idea is now clear. First, we are putting the soil properties, then structures, meshing, groundwater condition, and then staged construction.
Okay, ma'am, I have a doubt.
Yes.
So in the model itself, when you are assigning the properties of each layers,
Hmm.
then in the first layer is that is clay layer, right?
Yes.
The other two
First
are sand
layer is
layers.
clay layer. Yeah.
Clay layer, right?
Yes.
So when you're assigning the properties, do we have to give also the phi values or only c values? Because in the other two layers,
Hmm.
even though that is purely sandy soil,
Yeah.
you said we have to give some small value for c.
Yeah, actually,
Yeah.
for clay layer, when we define,
Hmm.
there is two analysis, like a long-term behavior or a short-term behavior. Suppose if we are having a short-term behavior, it is undrained, so it will be having only C value. Suppose
Okay.
if it is draining for long time and it is kept as such, then the clay layer will also, like the excess pore water pressure gets dissipated and some phi value will get generated. So in
Okay.
that case, we need to select, I think, undrained A. Then we have to assign a phi value also. In this undrained B condition, it is like a short-term behavior. So in that, we will only have the undrained condition,
Okay.
SU. So in a long term, even clay layer will also develop a phi value. So
Okay.
strictly speaking, when we do some analysis for a long time behavior, we have to model both and see which is going to be governing.
Okay. Then in untrained A, B, C, there are three conditions. So it's only based on the strength and stiffness.
Yes.
Okay.
Hmm. Okay.
Okay, ma'am.
Yeah. So this problem, I think we are now clear. So, okay, I'll just show some photographs. Like this is also excavation works. This is what we have seen now. This is a pipeline work. In this, even though it's a short depth, people have to go inside. So this has to be safe. It's a trench box. So such an analysis we can do in Plaxis. This one just I have shown like it's not a planned excavation. So we won't prefer to do this. Okay, yeah. And these are some photographs of some deep excavation works. Here what we see is sheet pile shoring system with struts and bailers. And here it is a secant pile system with struts. And this is another type of wall, contiguous wall with angers. Here, if you see, we don't have struts. So it is having back angers which goes into the soil and takes the strength. All such things we can model using Plaxis because we need to design what is the pile or what section of sheet pile is required to take it and what is the loads coming on this. So deep excavation means whichever excavation more than 4.5 meters. And analysis is important because it's a highly cost taking structure, because this is a temporary structure. Our main structure is coming only inside. So for this shoring work, we have to incur so much cost and time. So analysis is important. So I'll just show a small modeling. Deep. So if we cut a section here, it will have the pile walls and the struts in between. So what is represented here? This is the sheet pile and struts. There are different levels. So let us just see the modeling of one typical case, which is a 6 meters deep excavation with two levels of struts at zero point 0.5 and 3.5. And 8.5 is the embedment length of the sheet pipe. So here, whatever I'm telling is 6 meters. The excavation depth is defined. Remaining all we are checking. Like we are taking this sheet pile length of 8.5 and checking whether it is sufficient. If not, it's to be increased. So it's a trial and error procedure. And also this levels of struts is also an initial basis. So I'm keeping zero point 0.5 meters, and at 3.5 there is a strut. So we'll have this kind of support, one at zero point 0.5 and one at 3.5. And then there is the excavation and construction going to happen from the bottom. So this is how a procedure will be. First, there will be the installation of this retaining wall, and then there will be an excavation happening to the bottom of the strut level, and there's the first strut gets installed. Then they will go for the next excavation to the bottom of the second strut gets installed. Like that, it is a procedure. So it comes down and then the construction activity happens here. So this is the bottom up construction or cut and cover construction. So this analysis, we will just try to model. So this width of excavation is 10. So I have taken 5 and minus 5 and all the coordinates as such. So, okay. We have to, I'm taking the same soil properties. Now I'm not going to vary. So structure alone, we will just change. So here there is select multiple objects, select points, then it will select all the points in that, and we can delete. Now I have to create this pile wall, and this is the profile what we have to create. So the points first have to be defined. So create point. It's minus 5, 0, minus 5, minus zero point 0.5, minus 5, minus 3.5, minus 6, 0.5, 3.5, 6, 8.5. Then I'm just copying and pasting here. So all the points are just plus 5. Then I'm entering. Okay. Yeah. There were two brackets. That's why it was showing some error, unbalanced. Okay, so now the points we have defined. So this is the bottom point of the pile. So excavation bottom is this one. So I'll just put the line covering the excavation. So this is the ground level. This is the bottom of excavation. And just right click. So our points are defined. Now, for this pile element, we have to define a structure. So in this structures, create structure. Here there are different options: fixed in angle, create plate, geogrid, in the embedded beam row. Interface node to node anchor. For pile, it's plate element to be selected. So we have to click the top and bottom and right click. So the pile has got selected, created, but material is not assigned. That's why it's in shaded color. And struts also we have to define. So in this fixed int anchor, that is used to assign for struts. So at these levels we have the struts. I will like it should be in the reverse direction that we'll assign. So first let us give the properties. Yeah, before that, um, as we have seen in this slide, here we have the excavation done to some depth below the strut level. Say it's zero point 0.5 is the strut level, so excavation may be carried to 1 meters. Then only the people can stand and install the struts at this level. So there is an excavation happening to zero point 0.5 meters below the strut level. So we need to define that points also. Below the strut, there is points to be defined. So yeah, otherwise at one both sides, and then at 4, and also we need to give that line which is the excavation line. Now we have to assign the properties of the plate element. So in the soil, this is the materials tab. So in material sets, we whatever soil we have entered is here. Here we have drop down for plates, plate element, which is the pile. So for a sheet pile, I have just written down the properties. So this properties, uh, E and A value, like for sheet piles, we will have some standard cross-section area and moment of inertia. So based upon that brochures, we can find out what is this EI, weight of the pile, and Poisson's ratio for steel. Or if it's concrete, we need to assign accordingly. So I am just using these properties in this modeling. So it's a pile element. EA is an EI, weight of the pile, and new value. Okay. So pile properties are defined. Now if we go to the structures tab, we can just click it and drag to this pile. So it gets assigned to the pile element. So now we have to give the struts. So it's anchor, new, strut. So strut also we need to assume a initial strut and take this value. So it may be passing or not. So if it's not passing, we need to increase the sections. So everything is like trial and error method only. So this is L spacing. L spacing means presently I'm giving 1. What it means is in the Z direction, we have the struts at some spacing. So here if we see, there is a strut here, then maybe after 1.5 meters there is another strut, then here there is some space, and then the strut is like a diagonal strut. So it's like we cannot clearly define. So what we are going to get from Plaxis is like we are giving the struts, and whatever is the veiler load onto this veiler which is embracing this, so that is getting to be determined from Plaxis. So what we can assume is like the strut is available at every 1 meter, then we will get a veiler load per meter run. So I am just giving L spacing 1 as 1, or otherwise if you have a clear define, then whatever spacing is available between the struts in Z direction can be given. So I have assigned the properties of the strut. Now this strut has to have some length in this direction as well. So since our width of excavation is 10, we have to give 5 for this and 5 for this. So x direction 5, this also, and here, since the direction is to be reversed, I am giving -5, and here again -5. So now we have defined the pile and struts. Another thing what we have to remember is like at the interface between the pile and soil, there will be a reduction in strength. So presently we have entered the actual strength of the soil only. So there's an interface tab. This comes in picture in such cases when there is an interface of soil and structure. So here we have to give this strength as manual and R inter as 0.67. It is like similar to the delta value what we give, it's 2 by 3 of 5. So we are giving this reduction of 0.67. So it is to be taken only in such cases where there is a structure soil interaction. So in all cases, I am just giving that value of reduction. So whatever strength parameters we are entering will get reduced by that. This one. Okay. Okay. And so we have created the interface factor. Now interface we have to define. So here for structure, it's in structure, create interfaces there. From this pile top to pile bottom, we have to click. So it creates a negative interface. Then once we drag it up, it gives a positive interface one side. After clicking top, right click. So now there is an interface created and pile is assigned, struts are created. So now we can go for the details. Another thing is loading. So say I'm just giving a loading here. Uh, so this is -20 or -50, and depending upon any nearby structures, we need to give the loading. So our model is created. Now we can go for the meshing. Whichever is not calculated will have this star. So generate mesh. So this only will take some time. Okay. So meshing is done. Uh, just let me save this. Okay, since we are using the previous model, whatever excavation phase we have defined, it's already there. I am just removing it. Okay. So now in mesh, okay, after meshing, flow condition. So initial phase at ground level only, water is available. Uh, in the next phase, we want to lower it down. So, give me 1 second. Here we will create water, this point, then a point near to the excavation. It's lower down the bottom of excavation or to 1 meters below excavation, we can assume. Then we can select it and put make global. So for all further phases, this is the water table that will be considered. Now staged construction. In initial phase, this is the soil. There is no loading available. Directly it is the soil. So whatever we have given earlier, K0 procedure, that is sufficient. Now phase 1. First, as we have seen before, we have to install this piles and this loading also will come together. So just click here, activate. So loading gets activated, and if we select the pile, like each element should be clicked this way and activated. Otherwise, we have to give the select multiple objects, lines, plates. Then if we drag, all the plates get selected, activate. So initially, the procedure we have seen. First is the installation of the retaining wall. So that is what has been done. Installation of retaining wall. So will be pile installation. It starts from initial phase. It's a plastic analysis, and water table is phreatic. Next is first excavation is going to be done just below the strut level. As we have seen here, below the strut, excavation has to be done. So if we click here and right click, deactivate. So excavation has been done to 1 meters. I'll name it as first excavation. So it starts from pile installation. Next phase will be first strut, in which this strut has to be activated. Then next excavation will be proceeded. So in this, we have to deactivate. I'm just not changing the phase names. Here we have to activate. So that is the stage procedure, what we have to do. And this one, deactivating to the bottom of excavation. So now we have come to the bottom of excavation by staged construction. So once again we'll see initial phase, nothing is there. In pile installation, loading and the piles have been installed. Then first excavation, first strut gets installed, next excavation, second strut, next excavation. Now we can go for this calculation. So this is like a basic detail. If we have to see, like there is a backfilling stage also, like during the construction, the strut gets removed. So during that phase also, we have to check what is the bending moments and load on the remaining struts. So that thing is like more advanced. So this is sufficient for a basic idea. Okay, since factor of safety analysis is not involved, that's why it will run quickly, even if it's 5 or 6 phases. So it's completed. Now we can view the calculation results. So here we can see initial stage, then first excavation, pile installation, first excavation. We can see in each stage how much is the deformations. This is like total deformations 36 mm. Then strut gets installed. So each phase wise we can see. To get the bending moments on this piles, if we just double click on the pile, uh, since it's deformation activated, it's showing total deformations. What we have to select is forces bending moment. Then maximum bending moment value in that phase gets shown. Like that, in each phase, we can calculate and we can get the value. So in each stage we have to see what is the value, and based upon the maximum value, design has to be proceeded. Now to see the old window duplicate mod view. Here again, if we click the struts, uh, for the first strut, it will show what are the forces in like in each excavation, how the force gets varied that we can get. So usually, what procedure we do is like from Plaxis, we'll extract these results, what is coming onto the struts and uh, plate, and it will be given to a structural engineer for design of the struts. And so the structural elements gets designed by a structural engineer. The influence due to the soil gets determined by a geotech engineer. That is the procedure what we used to follow, but depends upon the industry where you're working. So I hope this is also modeling is also clear, at least a basic idea. So yeah, anything?
Ma'am, hello.
Yes,
Can you take
yeah,
the model, ma'am?
yeah, sure.
So here in this case, it is a vertical excavation. So when you
Yes.
are assigning a phreatic layer,
Okay.
the phreatic layer have some inclination, have some slopes
Yeah.
along this vertical directions on
Yeah.
vertical sides, right? So
Hmm.
how you are giving that
Yeah.
slopes for phreatic layers in the model?
Okay. Actually, just what we assume is like there is some 0.5 meters gap here. It's not like dropping straight because in case of sheet piles or secant piles, what we do is even after installation of this, um, there may be some gaps between these piles. So if there is water table even at the sides, it gets leaked into the excavation. So what when the dewatering plan is taken, there will be a deep well planned outside. So there is a dewatering inside as well as it will be taken outside as well. So that on the side of the excavation there is a water table drop. So that is usually planned. Unless suppose if it's a secant pile wall where it is more rigid and there is less chance for the water seepage, then we can take the water level vertically itself along with the pile. So if there is a dewatering point outside, then we can show the lowering this way. So it is dependent.
Okay, okay. So what is the maximum extent, what is the maximum slope that can be provided
Like
at
it
the
is
dewatering condition?
okay. It is preferable to go for a conservative design.
Mm.
So we usually take like 0.5 meters away itself. But in actual site condition, we may have a dewatering point at some 1 meters away or 1.5 meters away. So actual drop point may be even far. So to be more conservative, it can be taken at 0.5 meters away from the wall.
Okay, ma'am.
Okay. Yeah, that's the modeling part what I have. And so overall, if you see the summary, our points are defining the boundaries and finding the coordinates for defining the structure. Then creating the soil model, entering structure details and the loading details. Then mesh generation, defining the water table, staged construction. Then results and providing it to the structural engineers. Yes, so that's all what I have for today's session.
Any other questions from the faculty side?
Jinu, I have a
Yes.
question. Can we apply this package for the design of structures also, or only for soil properties? Soil.
This is basically for soil structure interaction only. For Bentley only it has STAD Pro. So that is mainly used for the structural design and details.
No,
Plaxis
soil,
is,
soil, soil structure interaction, but there the foundation design is there for the
hmm,
design of say isolated footings or something like that, because that also is a soil
okay.
structure interaction. Can we do that also using this package?
As far as I know, like we can get the settlements. Like suppose if we model a footing, we can get the settlements. But what is the design like steel required for that? Those things we cannot do. That's what I understand.
Okay. In the model given, I think there are three layers for the soil. In the figure that
Yes,
you have shown there,
yes,
one, two,
yes.
three layers. What about the bottom layer? What property is given for the bottom layer? This is a bottom
Bottom layer I have taken like dense sand.
dense sand.
Yeah, yeah. This is the properties which is taken with phi value of 35 degrees.
Now, is there any difference if you are taking it as a hard soil? That's a hard
Yeah,
rock, a hot rock.
yeah, there will be difference. Like in that case, we won't be having only phi value. In that case, there will be some cohesion value also to be assigned. Like if in case of rock, directly C5 value, like soil, we cannot give. There is another model called as hook brown. So using that, like rock will have the strength, no? So using the RQD or strength properties, we need to, and also it will have joints. So all such things comes together, and from that hook brown analysis, C5 will be determined, and then it can be used in here. It will have some C and phi both. And also when we give this embedment, if it is like a rock, then we may not go this much deep into it, like installation wise, or the embedment requirement will be less. It may be just zero point 0.5 into the rock. So that is in the model point of view, and also soil properties point of view, it will be different.
In the model that you have done here, shown here, whether we will get the moment values also, moment and shear values.
Yes, for this secant pile wall, I mean what the wall we are using here, I taken sheet pile. So by double clicking this one and giving forces, here we can get this maximum and minimum bending moment values for different stages. And also shear force values can be obtained.
I'm actual force also. Axial force.
Here actually the main, it is a retaining wall. So mainly it is having only this bending moment and shear force, like axially loading is not there. Only it will be the self weight.
Okay, thank you.
Yes.
Any more questions, please? I'm requesting you all to please ask questions if any. Otherwise, we can wind up. Sudhi?
Yes, sir.
Okay.
Faculties, if you have any questions, you can ask. No. So, shall we wind up the session, sir?
Yes, yes.
Okay.
Okay, thank you
So,
so much.
so Jinu ma'am, it was a very informative session. So,
Yes,
within the
thank you.
limited time, you have explained two modeling systems in Plaxis 2D software. So, uh, thank you so much for your valuable time. And I thank all the faculty members and our respected HOD for actively participating in the session. So, thank you all. Thank you so much.
Thank you all.
Thank you, Jinu, once more.
Thank you, sir. Thank you for giving this opportunity.